Yeah. Hi, Ankit. This is audible,
Yes, sir, it is
and the screen is
visible and
also visible,
audible.
right?
Yes, sir, it is visible and you are
Okay.
audible as well.
Okay. Okay. Let's start. Okay. So, good evening. Welcome to week 9 of Theory of Computation problem solving sessions. So, this time's topic is complexity, introduction to complexity theory. Okay. So, it's an really interesting area. In fact, this is the area of my research. Uh, So we'll come to complexity theory, but first we'll solve a few questions on assignment 8. Okay, the previous assignment. So the previous assignment was based on undecidability and reducibility and so on, right? So we've picked 3 questions which are of particular interest. So we'll solve them one by one. So let's look at the first one. Okay. The question says choose the true statements. Let B be such that EQTM reduces to B and A bar TM reduces to B. Okay, B is a language. Okay, B is a language. What is EQTM? EQ stands for equal. Equal Turing machine is the set of all Turing machines, set of pairs of Turing machines. So that given two Turing machines, M1 and M2, uh, language of M1 is equal to language of M2. In other words, it's the pair of all Turing machines whose languages are identical. In terms of a decision problem, the input is the input given are two machines, two Turing machines, and we want to check whether the languages of the two machines are same or not. Okay, that is EQTM. Now, what is ATM bar? First, we'll look at ATM. Okay, because it's just a complement of ATM. So ATM is given a machine M and an input X, whether M accepts X. Okay, M is a Turing machine and X is an input to the machine M. Okay, so the decision problem version would be given a machine M and an input X. Okay, does M accept X or not? So that is the decision. The language version is it's set of all the pair of M and X. Okay, such that M accepts X. So what is ATM bar? ATM bar is nothing but MX. Okay, so it's just a complement of ATM. It will consist of all pair of M and X such that M rejects X. Okay. So you may have seen in the lectures, okay, that uh, EQTM actually reduces to ATM bar. Okay, the construction is there in the next question, so right now I'm not doing it, but the construction is pretty simple. But in the lectures, it's mentioned that okay, checking for if two Turing machines have the same language is uh, is as hard as determining ATM bar. Okay, and further, I want to show this. Okay, that say this is the set of all decidable languages. Then it is contained in the set of all Turing recognizable languages, and it is also contained in the set of all Turing co-Turing recognizable or co-recognizable. Okay, and everything outside decidables are what is known as undecidables. And Turing recognizable languages are those languages which have a Turing machine that recognizes the language, which means if if an input belongs to the language, the Turing machine will definitely say yes. But if it does not belong to the language, the Turing machine may say no, or it may loop. It may never halt. And core Turing recognizable languages are those languages which have Turing machines which will always say no if the input does not belong to the language. But on a yes instance, that is when it belongs to the language, it may actually loop. And it may say yes also, but it may loop also. And or in other words, if L is a language in if L is a language here, then L bar will be here. Okay, it's the same thing. Okay, L bar will be here. Okay, and if L is a language here, then L bar will be here only. So let me call it L1, L1. Let me call it L2, L2. So if L2 belongs to decidables, L2 bar will also be contained inside decidables. Okay. And what is decidables? Decidables are those languages which have Turing machines that will correctly say yes and no each time. It will never go in an infinite loop. In other words, this is the set of all languages, set of all problems that have algorithms. Okay. So now let's look at this question. Let B be such that EQTM reduces to B and A bar TM reduces to B. Okay. Now the question says, does ATM reduce to B? That is the question. Now, okay, I made a mistake here. So this is the other way around. Okay. ATM can be reduced to EQTM. ATM bar. Okay. So ATM bar reduces to EQTM. Okay. And so now we are saying that first we'll look at this. B is decidable. Okay, let's check this. Is it true that B is decidable? Let's see what happens if B is decidable. If B is decidable, if this becomes decidable, then what happens? Then the fact that the reduction exists from ATM bar to B means that ATM bar becomes decidable. And since decidable languages are closed under complement, ATM becomes decidable. But we know that ATM is strictly contained in here. ATM is here. It is not contained in decidable. So it cannot be that B is decidable, because then it would mean that ATM would become decidable. Okay. So this is not an option. Next it says B is not recognizable. Okay. Let's see what happens if B is recognizable. Okay. Suppose B is recognizable. Okay. Suppose B is recognizable. Then what would happen? Then, but see, suppose B is recognizable, but A bar TM is not. It's not that it's not. Yeah, it is not recognizable. So it's actually co-recognizable. Right. A bar TM is here. Because ATM is here, A bar TM is here. And what are we saying? Let's say B is recognizable. Okay. And but ATM is co-recognizable. So here we have an example of a co-recognizable language reducing to a recognizable language. A yes goes to a no, no goes to a yes. If it is both recognizable and co-recognizable, then your language should be here. It should be decidable. So it would mean that ATM as well as A bar TM are decidable. So it cannot be recognizable, and therefore B is not recognizable. Now finally, what do you have? The language B bar is decidable. Okay. Again, it's the same answer, that if B bar is decidable, since you can, if B bar is decidable, its complement, okay, that is B, will also be decidable. And we know that B cannot be decidable, then the language B bar can also not be decidable. Okay. And finally, you have ATM reduces to B. Uh, Here, I think there is a slight mistake in the question. I just saw this right now because ATM bar reduces to EQTM. It's not that ATM reduces to EQTM. So I feel like what they are asking is this. I need to clarify in the next class. Okay, but I feel this is what they are asking. And since if you say A reduces to B bar, it means that, or A reduces to B, it means that A bar reduces to B bar. It would mean that if ATM bar reduces to B, just complement both sides. It is ATM reduces to B bar. Okay. So, okay. Yeah, Ankit, is it clear?
Yes, sir.
Okay, good. So, yeah, this part I'll clarify. I think they mean B bar, but okay. So, yeah, let's look at this. They're saying consider the following reduction function f that takes as input strings of the form mw and returns strings of the format m1, m2. So what happens is, see, there's a reduction f, okay, that takes in m and takes in m and w, okay, and gives two outputs m1 and m2, okay, where m1, m2 are Turing machines and w is a string. Now consider a function f that, yeah, this, okay, where m1 is a Turing, okay, so m1 is a Turing machine that rejects all strings, okay, m1 rejects all strings. So this Turing machine is just simple to construct. What you do is the algorithm is just like whatever w is, you just reject. So description is just reject anything, any input. Okay, and Turing machine M2 accepts all strings x in sigma star if m accepts w. Otherwise, it does not accept any string x. So M2 is defined as follows: if so M2 description of M2. Okay, if m accepts w, okay, if m accepts w, then what happens? M2 accepts all strings in sigma star. M2, okay, accept any string, which means if M2 is given an input z, okay, the input to M2 is z, then accept z trivially. Okay, so if the m given, if m given is accepts w, okay, is m, if m given is supposed to accept w, then what happens? M2's behavior is that it'll accept any z given to it. Okay, and whereas if m does not accept w, so it does not accept means m, remember m may loop also. Okay, m loops or rejects, then what is it saying? Otherwise it does not accept any string, then reject z. Any z you give, it will reject if it loops or rejects. Okay, now what is it saying? Ram, okay, claims that this reduction is not, by the way, this is how m1 and m2 are defined. Okay, given mw, this is what m1 and m2 will look like. Okay, Ram says that this reduction is not valid. Why? Because this is not a halting computable reduction. Remember that. How did you define reduction? A reduces to B if x is in A for all x in the language. X is in A, okay, not for all x in sigma star. X is in A if and only if sigma of x is in B. Okay, there exists sigma, and this is the reduction. This is the f here. Okay, and what is sigma? It should be computable by total Turing machine. that is the sigma, that function, okay, the reduction should always halt, okay, given any input. And because this is not a halting computable reactions, since it checks whether W is accepted by M, and this check may lead to a loop in the computation of F. Now what Ram is saying is, okay, but it is how M2 is defined is as follows: it runs M, okay, and checks whether M accepts W or not. But Ram is saying that what if M was did not halt on W? What if M did not halt on W? And this M2 would just keep looping, right? If you ran M on W. So how can it be that this reduction is total? How can it be that this reduction is computable by total Turing machine? So Ram is saying that this is not possible. This is not a valid reduction. So and this check may lead to a loop in the computation of F. That is what Ram is saying. So that's why the statement says, okay, Ram is false because ATM is recognizable and therefore reduction to is halting computable, and so on. But anyway, main thing we want to answer first is this a valid reduction or not? The answer is actually it is a valid reduction. It is a valid reduction because we are not actually running M on W. What do I mean is that we are only giving the description. We are just writing it on paper. We are writing it on the tape. Okay, we are not actually running it. We are not actually running it. Only giving the description. And writing this description will not loop, right? Everything to make a Turing machine that always rejects is always decidable. I mean, it will not take infinite time to come up with a machine that does this. We can program it to do that way. And similarly, writing the description of this does not take infinite time to do. Okay, and writing description can be done in finite time. So all we are doing is writing the description. We are not actually running it. Okay. So RAM is false because ATM is recognizable. Therefore, the reduction is halting. Okay. So the reduction is valid. It is valid. It is valid. But this we need to check. Okay. Reduction shows that EQ is not Turing recognizable. Let's check that. Okay. So they are saying it shows that ATM reduces to EQTM. ATM, what does it do? It accepts, it takes MW and M accepts W. And what is EQTM? It takes M1, M2 and checks if language of M1 is equal to language of M2. Right. So now what we are saying is, okay, EQTM, okay, ATM reduces to EQTM bar. And here we have the F. Okay, what does ATM take? It takes out M and W. F translates it into M1, M2. And we can see F translates into M1, M2 such that M1 and M2 satisfy these properties. Okay, and M1 rejects all the strings, and M2 accepts all the strings only if M accepts W. And so this guy says yes or no whenever EQTM says yes or no. So is this reduction valid? They are saying. Let's check. Okay, we want to show that if X is in ATM, then F of X is M comma W is an ATM, then F of M comma W is in EQ TM bar. So what is EQ TM bar? Sorry, EQ TM bar would be not equal to. Their languages are not equal. So we'll show this now. How? Because MW is in ATM means that M accepts W, and this FMW is nothing but M1 comma M2. Okay. Now, if MXW accepts, then what happens? M1 is always defined to reject all strings. Then M1 is always rejects all strings. But now what do you have? What does M2 do? M2, since M accepts W, okay, because it was in ATM, MW is in ATM, it will accept all Z, any Z that you give. How does M2 behave? M2 accepts all strings. So what is the language of M1? Since it rejects all the strings, the language is empty. Okay. The language is empty, and M2 accepts all strings. So if it accepts all strings, then what is the language of M2? It is sigma star. So is L of M1 not equal to L of M2? That is the question, and the answer is yes. So EQTM, so M1 M2 belongs to EQTM. That is F of MW belongs to EQTM, and sorry, EQTM bar. They are not equal. The languages are not same. And similarly, you can show that if M comma W is not in ATM, that means M does not accept X. M does not accept X. M does not accept W, sorry. Then you can say that M1 rejects all strings and M2 does not accept any string. And then you can say that, okay, so L of M1 was already 5, but since M2 also does not accept any string, then L of, sorry, M2 is also 5. So hence L of M1 equals L of M2. So this means that M1, M2 is not in EQTM. Okay, you have this. Okay, so you've shown that it reduces. You've shown this. So what does it mean? This means that ATM reduces to EQTM bar. Now ATM reduces to EQTM bar. This is correct. Now I've mentioned before that. Oh no. Yeah, I've mentioned before that if A reduces to B, then B also A bar reduces to B bar. So just complementing both sides is always valid in a reduction. This is also true. And this reduction shows that EQTM is not Turing recognizable. This is also true. Why? Why is this true? Because say EQTM is Turing recognizable. Okay, say EQTM is Turing recognizable, and we have that ATM also reduces to EQTM. ATM bar also reduces to EQTM bar. It would show that EQTM is decidable. And if EQTM is decidable, then it would show that ATM is also decidable, ATM bar is also decidable, but that is clearly not the case. Both are well known non-decidable languages. Okay, so this goes to show that EQTM, okay, even though ATM is, we have examples of languages that are not decidable, okay, which we call undecidable languages, and which we have Turing recognizable languages. We are showing that there are much more harder languages also. For example, EQTM is a very hard language. It is not even Turing recognizable. It is it has a harder difficulty than Turing recognizable. Okay. So, okay, I hope that was not too fast. Is it fine? Okay.
Yes, sir.
Yeah. Okay. Okay. So this is the final question from the assignments. So the question says pick all the statements that are true. So if okay, what it's saying is as follows. Okay. If A reduces to 0 star 1 star, then A bar is recognizable. Okay. If A reduces to 0 star 1 star, then we cannot have that EQ TM reduces to A and so on. Okay. Let's look at the first question. Okay. A reduces to 0 star 1 star. Let's look at this language 0 star 1 star. Can you tell me about where does it fall? What kind of language is 0 star 1 star?
Sir, it is non-regular.
It is a known regular language. So
Yes, sir.
it has a corresponding DFA. Right?
Yes, sir.
So if it has a DFA, then obviously my Turing machine can just mimic the DFA, and then the Turing machine will always, halt in that sense. Another way to look at it is total Turing machines can always be viewed as algorithms. You can always check whether you can always make an algorithm that checks whether a given string is of this form. It's very simple. You just keep scanning the string from left to right. Right. Let's say you are writing a C++ program or a C program. Okay. You just keep scanning from left to right, and as soon as you see the first one, not as soon as you see that zeros end, you check if there are only ones coming. If you ever see a zero here, then you will say no, and so on. So that is another way to say that this is decidable. But the important thing is it's regular. It is a known regular language. It has a DFA, and therefore it has a total Turing machine, which means that 0 star 1 star is decidable. It is always decidable. I'm given a string, whether I can check if it is of this form. It is saying A bar is recognizable. So A reduces to a decidable language. By the definition of reduction itself, it means that if my right hand side is decidable, my left hand side becomes decidable. That is what we were saying right before, when we were saying ATM reduces, many one reduces to EQTM. We were saying that if EQTM bar, if this is decidable, if in some world it is decidable, then this guy becomes decidable. So by this we have that 0 star 1 star is decidable. A reduces to the decidable language, which means that A is decidable. Now, since A is decidable and complements of decidable languages are also decidable, this means that A bar is decidable. And this follows from the fact that you can flip yes or no. You can change the final states to non-final states in a Turing machine. Okay, so next, what do you have? If A reduces to 0 star 1 star, then we cannot have that EQTM reduces to A. Now again, if A reduces to 0 star 1 star, A becomes decidable. We cannot have that EQTM reduces to A because A now becomes decidable. If A is decidable, EQTM also becomes decidable. But that is clearly not true. We've already seen that EQTM is such a difficult language that it is not even recognizable. Forget about decidable. Okay, so this is clearly undecidable. This is not true. So the first one is correct, the second one is wrong. Next, if A reduces to ATM and A reduces to A bar, then A reduces to 0 star 1 star. Now this also can be seen that, okay, A reduces to ATM. Yeah, okay. Or more essentially, look at this. A reduces to ATM means that A is at least recognizable. Okay, A is recognizable because this guy shows decidability, and this will always halt in the yes instance, meaning the entire reduction will halt in a yes instance. It may not halt in the no instance. So A is clearly just recognizable. But we have that A reduces to A bar. What does it mean? A reduces to A bar means that given A, I can decide A bar, or given A bar, I can decide A, which means that A needs to be decidable. This is another property of recognizable languages. And if A is decidable, then A will always reduce to 0 star 1 star. Now this might seem strange, okay, but every decidable languages are reducible to each other. Okay. Because see, A could be anything, right? A could be any decidable language. Let's say A is decidable. This would mean that there is a total Turing machine deciding A. Let's call it M. So what will we do? See, what we'll do is, given an input X, we'll run the machine M. M says yes or no. Okay, yes means it belongs to A, no means it does not belong to A. What we'll do is construct Y equals, if it's yes, construct Y equals 0, 0, 1, 1. If no, then construct Y equals 0, 0, 1. Now this Y, give it to 0 star 1 star solver. Now treat this as your F, treat this as your reduction. It takes an input, okay, it's doing the same thing. It takes an input meant for A, okay, and it converts it to an input meant for 0 star 1 star. Now if X belongs to A, M will always say yes, and it will construct a language which is in 0 star 1 star, and this solver will say yes. And this guy, if it is not in A, okay, it is not in A, then M will always say no. Then we'll construct 0, 0, 1, which is clearly, oh, okay, sorry, 0, 0, 0, 0, 0, 1, 0. Okay, yeah, this is not in 0 star 1 star. So this is not in 0 star 1 star, and therefore it will say no. So the idea is it says that, you know, trivially we can say that every decidable language reduces to each other. Okay, and so this is always true. Finally, if A is decidable, then A reduces to 0 star 1 star. That again we've shown the same point again. So this is clear. Okay. Okay, Akshay is here. Hi, Akshay. So yeah, so we've just seen the final question for the assignment section. Now we'll be moving on to the next part for this week. Okay. Okay. There is one more question here. What is the time? 6:50. Okay, no problem. This is actually a simple problem, so I want to show this. Okay. I'll skip to this week's part, or do you guys want me to do this question, or is it fine if I skip this?
Sir, can I please explain briefly?
Yeah, I should explain, right?
Yeah, briefly.
Okay, great. Okay, I'll explain it. No problem. Okay, so the question says as follows: for any language L and a string W, define LW as follows. Okay, LW is the union of L and W. So see, note that this language L, okay, may also contain W, but that is not a problem. We are just forcefully entering, or if it already contains W, no problem. It will just be L equals LW. Okay. Again, I'll repeat it. Given two languages, given a language L, okay, I have a language which is a bunch of strings, okay, and a string W. LW is just the language L, and where we are including the string W to it. Okay. Again, I'm saying that L could already have W in the beginning, but if it already has W in the beginning, no problem. L will be equal to LW. Okay. Example. Say L is 0. Say L is 0. L is 0 to the n, 1 to the n. Okay. And W is say 0, 1, 0. Okay. So LW will look as follows. It will contain 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, and follows along with 0, 1, 0 somewhere, and then so on. So we are including the string W also in LW. Clear? Now we are saying, let's say L is Turing recognizable. Then this implies that LW is Turing recognizable. What is meant by Turing recognizability? There is a Turing machine which will say yes if the string belongs to the language, and if the string does not belong to the language, then it may loop or it may reject, no problem. But if it belongs to the language, then definitely the Turing machine will say yes. Okay, and the next says if LW is a Turing machine, LW is Turing recognizable. Okay, LW, this guy is Turing recognizable, then L is Turing recognizable. So the question is, are both true? Is one of them true, or are both of them false? That is the question. Let's see. Let's try to prove them one by one. Okay, statement P. Let's try to prove statement P. L is Turing recognizable, LW is Turing recognizable. Let's see. Statement P. L is Turing recognizable, then LW is Turing recognizable. Okay. What does it mean to say that L is Turing recognizable? L is Turing recognizable means that there exists a Turing machine that recognizes L, which means there exists a Turing machine that accepts if X belongs to L and rejects or loops otherwise. Okay, and similar definition here, there exists a Turing machine that accepts some Y, okay, if Y belongs to LW and rejects or loops otherwise. Okay, now let's say we'll assume, okay, we want to prove this statement, right? We'll assume that L is Turing recognizable, and which means that there exists a Turing machine and so on. So we'll say, okay, okay, which means that there exists a Turing machine. We'll call M the Turing machine, okay, and that accepts X if X is an L and rejects, and this is what we call recognizes, right? That recognizes L. There exists a Turing machine M that recognizes L. Question is, can we build a Turing machine that recognizes L bar? That is what this statement means. No, we want to prove this. Can we show a Turing machine that recognizes L, sorry, not L bar, LW? This is the question. And the answer is yes. Okay, we want to build a Turing machine that recognizes W. It is simple. What we'll just do is, see, half of the job is 90% of the job is already done for us because we already have an M that recognizes L. So given any L, so clearly L is a subset of LW because LW is defined to be L union W, right? So LW already contains all the strings in L. We are just including W to it. So clearly L is a subset of W. L is a subset of LW. The only thing that might not be in L, the only string that might not be in L is W. Only W may not be in L. So half of the job is already done. We already have a Turing machine M that recognizes L. Okay, so we can recognize all the strings here. We just need to go one step further and recognize whether W is the input W or not. Okay, so here is what we want to do. Okay, so define M prime, okay, as follows on an input X. Okay, what we do is check if, okay, let's start with run M on X. Oh, sorry, this is a bad idea. First, what you want to do is check if X equals W. If yes, then accept. Okay. Next, what you want to do is, if yes, it is equal to, next what you want to do is run else, okay, run M prime, M on X, okay, and if yes, then accept. This is all that is there, and this will show that LW is recognizable. Why? I'm proving now. Okay, why does this show that LW is recognizable? We have that L is recognizable. Okay, this is was an assumption, right? We want to show that LW is recognizable. This means that if, okay, X belongs to L, then M will definitely say yes. M accepts. M will never loop. So that is what is happening. If M prime, okay, this new machine that we constructed, if M prime were given an X that is in L, then first it would have checked if X is in W. Okay, X is equal to W. But let's say X is not equal to W, it goes next. Okay, what it does is it runs M on X, and if X is in L, then M definitely accepts. If M accepts, then we are accepting. Oh, if M accepts, that's a better. If M accepts, then we definitely accept. Then M prime accepts X. Okay, which means that X is in the language of M prime. Okay, next, okay, this is the first part. Okay, next part is if X is equal to W. Okay, then what happens? If X is equal to W, then what we are doing is, if it is the case that x is equal to w, then m prime will accept. M prime will accept. M prime accepts m equals w, right? Okay, I need to charge my laptop. Okay, after this. So m will definitely accept, right? Now, if m prime accepts w, w is in the language of m prime. So x is in L for all x is in L. Okay. So what kind of strings does it accept? It accepts all the strings in L, and it accepts all the strings that are equal to W. What does it mean? It means the language of M prime is equal to L union W, which is nothing but LW. And clearly this shows that this is recognizable. In the if it belongs to the language, if it belongs to LW, my Turing machine will always halt and say yes, will always accept. So this means that LW is recognizable because I gave a machine M prime which will always accept when the string belongs to the language. Okay, it may halt in the no case, that is not a problem. For example, if x is bad, okay, x is not in LW, then it may be so that for that bad x, m may loop, oops, m may loop, and therefore this entire thing will always loop. But that is not a problem because it didn't belong to LW anyway. Okay. Next, so statement P is clearly true. Next, it's saying LW is Turing recognizable, then L is Turing recognizable. LW is Turing recognizable, then L is Turing recognizable. Okay. Yeah, so this idea is also straightforward. Again, LW is all L union W. Right. Now we are saying LW is Turing recognizable, which means that there exists a there exists a Turing machine that recognizes LW. So if the input is W, it will definitely accept, otherwise it will reject. Okay. So L is Turing recognizable. So here we need a slight knowledge about L. Okay. So we assume W does not belong to L. Let's say this was the case. Okay. Then I'll give a Turing machine and assume W belongs to L. Then I'll give a Turing machine. Okay. Let's do this case. If W is in L, but let's say W is in L, but W is nothing but L union W. But L is already containing W, right? If I do union W, it won't do any effect to it. So this is nothing but L, because W is in L. Because W is in L. This shows that LW is equal to L, but LW is Turing recognizable. And there is a Turing machine which recognizes it. But these two sets are the same. So this implies that L is Turing recognizable. But suppose say W is not in L. Okay, suppose say W is not in L. Okay, 16. Yeah. Suppose say W is not in L. Then what happens? Suppose say W is not in L. So here's how we make a Turing machine for M prime. Okay, for L. Okay. M prime on input W, on input X, sorry. And let's say since LW is Turing recognizable, let's say the machine that recognizes LW is called M. Okay, M is a Turing machine that recognizes LW. So what we'll do is we'll simply check if the input X is equal to W or not. If it is equal to W, we know that W should not belong to L. Okay, so we'll say reject and halt. M prime will not accept W. But otherwise, what we'll just do is run this M prime, this guy. Okay, run M on X, and if accepts, then accept. Now, what is the correctness of it? What is the correctness? Why is this correct? Okay. See, W does not, let's say the input X, okay, is equal to W, then what happens? This means that X is not in L, right? Because W is not in L. Next, if X is equal to W, then what happens? M prime will do this check if X is equal to W or not. When it does this check, it will say reject and halt. So M prime rejects. Okay. Next, what happens? So this is the first case. Second case, X is not equal to W, or actually that's understood, X is not equal to W. Let's say X is in LW. Okay. And X is not equal to W. Okay, let's do this also. X is not equal to W. Okay. And X is in LW and X is not equal to W, then what happens? Okay, X is in LW and X is not equal to LW. Then if X is in LW, since this is the machine, if it is not equal to W, then this step 1 will be executed and we'll move to step 2. Okay. Then step 2 reached. Why is step 2 reached? Because it is not equal to W, so this step will, this guy will not execute. This guy will not execute. We'll go to this step. We'll run M on X, then accept. Then what happens? M prime accepts X only if M accepts X. M prime X accepts X only if M accepts X. And we are allowing all the strings except W here. So what happens? This means that the language of M prime behaves exactly like M without W. And what is L of M minus W, which is nothing but L minus W, LW minus W, which is nothing but L. So M prime is a machine. Okay, M prime is a machine that accepts exactly those languages. Okay, accepts exactly those languages which are in L, which are not equal to W. Okay, and since W did not belong to L anyway, M prime actually decides the language L. If W is in the language, then it's identical. Okay, so is this clear, Akshay? Just let me know if you want me to repeat anything.
Yes, sir.
Clear, right?
Yes, sir.
Okay, good. Just give me 1 minute, okay? I need to charge my laptop. Give me 1 minute. Okay. Is it charging? Yeah. Okay, good. Okay, I think I stopped presenting. Yeah, you can see my screen, right?
Yes, sir.
Okay, but there's a uh, so now we are moving to the complexity part. Okay. So complexity theory is, so we've seen decidability, undecidability, and so on. Complexity theory is a deeper dive. Okay, it is we are concentrating only on decidables. So as we saw, there are recognizable, unrecognizable, and there is decidable. Okay, decidables are those which have algorithms. So we are saying, why not focus on only those which have algorithms? Okay, and it is a study of decidables, and since everything is decidable, it has since we are focusing on everything that are decidables, and we definitely have algorithms for it. How efficient we can make the algorithms, that is the question here, in terms of time, space, and so on. Okay, so here's the question. Okay, so I hope you have seen in the lectures that the class P is all languages with deterministic polynomial time Turing machines, and the class NP as all languages with non-deterministic polynomial time Turing machines. So NP, the Turing machine, non-deterministic Turing machines, are similar to non-deterministic finite automata. Okay, where you can sort of move to several states at once, and if a solution exists, if a accepting path exists, then definitely the automata will say yes, right? That is what non-deterministic automata was like. And you have P and NP here, and P is all deterministic polynomial time languages. What is polynomial time? Time taking something like order n to the square, order n cube, and so on. So these kind of languages are P, and NP is all languages with non-deterministic polynomial time Turing machines. And another way to define NP is all languages with deterministic polynomial size certificate. All languages with polynomial size certificate. Okay, all languages with polynomial size certificate that can be verified in polynomial time. I have small certificates that can be verified in polynomial time. In other words, P are those languages which are easy to solve, and P are those languages which are hard to solve. Now the question is whether P versus NP. Is P equal to NP? Okay. Is P not equal to NP, and so on? All that is known is that P is inside NP. This is all that is known, and you might have seen in lectures that this is a huge problem in complexity. It is a huge problem in computer science and mathematics in general, and we still don't know whether P is equal to NP or not, or P is not equal to NP or not, but the general belief is that P is not equal to NP. Anyway, we'll do that later, but here's the question. Okay, define a class cop as follows. Okay, cop is a set of all languages such that the complement of the language is in P. Okay, what is meant by the complement of language in P? The complement in the language of the language L has a deterministic polynomial time Turing machine solving L bar. Okay, a Turing machine that always takes polynomial time, or in other words, an algorithm that always takes polynomial time. Now, question is it true that P is equal to cop? That's the question. Okay, and answer. So if I'll repeat it, if you have a language, if you have a problem that can always be decided in deterministic polynomial time, this is important, deterministic, no non-determinism here, polynomial time, then is it true that I can always do copy in polynomial time? Okay, so in other words, say if a language L belongs to copy, is it true that L belongs to P and the other way around also? So this also. Okay, is it true that if L belongs to P, then L belongs to copy also? Okay, now the answer is yes. Why? Suppose L belongs to OP. Okay, which means L bar belongs to P. If L bar belongs to P, then what does it mean? L bar has deterministic polynomial time Turing machine, say call it M. Okay, M solves L bar. Question says if L is in P, that is, if L is in P, which means does there exist a Turing machine which is deterministic polytime such that and call it M prime, okay, such that M prime solves L? That is the question. Getting it? Yes, the answer is yes, because see, L bar is decided by M. Okay, we want to form an M prime that solves L. Okay, M solves L bar. We will show a machine M prime solving L. Okay, and M prime is very simple. Here is the description of M prime. Description of M prime. Given input X, what it does is run M on X. Okay, run M on X. If M accepts X, then reject. If M rejects X, then accept. Okay. Why is this correct? Why is this correct? That is, why does it solve L? Let's say X belongs to L. which means x does not belong to L bar. If x does not belong to L bar, then M, which solves L bar, will accept it, right? M accepts x because M solves L bar. So M accepts x because x does not belong to L bar. Oh, what am I saying? Sorry, M rejects L bar. Because it does not belong to L bar and M solves exactly L bar. If M rejects L bar, then what does M prime do? If M rejects L bar, M prime accepts. Right, this is M prime. M prime accepts x. And M prime was supposed to accept x because x is in L. Now let's say x is not in L. What happens? If x is not in L, then x, by definition of L bar, it does not, if it does not belong to L, then it belongs to the complement, right? It is outside L. So x is in L bar. Okay. In case you are wondering. Why? Because L bar consists of all the languages which are not in L. All the x such that x is not in L. So by definition this follows. Next, if x is not in L bar and M is supposed to, sorry, x is in L bar and M is supposed to decide L bar, M will always accept. Not L bar, accept the string x. If M accepts the string x, then what are we seeing? Then reject x. M prime rejects x. So if x is, so now see, x is in L, then M prime accepts x. If x is not in L, M prime rejects x, which means that M prime decides or computes exactly the language L. So we showed an M prime that solves L. This is not complete because we want to show that M prime is also deterministic polynomial time Turing machine. But since M is already a deterministic polynomial time machine, and I just added one step to it. I added one step to it. See, this running will take some polynomial time. No, this takes some polynomial time on the input. Now to it, I'm just adding this constant time. This checking will only take some constant time. And this will take order one time. So M prime runs in polynomial time. Deterministic polynomial time. Why? Because there's no non-determinism here. I am not guessing anything. Okay, I'm not making non-deterministic guesses. And because M is also deterministic, this entire thing is deterministic. Okay, so now we've shown that if L is in co-P, then L is in P. How do we show the other direction? If L is in P, same thing we do. If L is in P, we have a deterministic polynomial time machine for L. Now we want to decide L bar in polynomial time. We'll just run the machine, and then if you say no, if the machine says no, we say yes. If the machine says yes, we say no. And this entire machine runs in polynomial time, deterministic polynomial time. So it is true that P is equal to co-P. Okay. So in other words, we say that the class P is closed under complementation. Okay. Is it clear?
Yes, sir.
Clear, right? Let me know if there are any questions. Okay. Just a small remark. Similarly define NP and COP. Whether NP and COP are same, okay, whether NP and COP are same is not known. P and co-P are, oh sorry, co-NP. This is not known. P and co-P are known, right? P is nothing but co-P, but this is not known. And try to do the same construction. Okay, the same construction that we did before. Yes to no, no to yes will not work. Previous construction will not work. Okay, and well, why it will not work is also, see, what we were doing in the previous case was that, see, our machine was deterministic. So if you make a computation path for it, okay, from this configuration it is going to this configuration, this and so on. It is deterministic. We can always predict, right? And if it accepts, we make it into reject. And same thing, if it rejects, we make it into accept. This is how it was working. No? So this is the computation path. If my machine is non-deterministic, there will be multiple paths. I'll be guessing all the way. I'll be making non-deterministic. Recall how a non-deterministic DFA works. Okay, so I'll be making these guesses, and here I can reject, here reject, and somewhere I'll accept. And what do you say about non-deterministic machines? Even if there is one accept, our machine will accept. Right? Even if there is one accept, our machine will accept. Now, if I convert it, if I do the same business, if I turn reject into accept and accept into reject, if I turn accept into reject and reject into accept, what my machine is non-deterministic. Acceptance condition is still same. Remember, here also I didn't change the acceptance condition. The acceptance condition is still same. Acceptance condition is still same in a sense here that even if there is one accept, my machine will accept. So here I found one accept, and here I found one accept. So if I give an input x, okay, if I give an input x and check whether it is there in the language or not, since there is a single accept, since there is at least one accept, I will say, okay, I'll accept. It belongs to the language. Now, this is the construction I do for L bar, that is the complement of L, and I have flipped all the accept and reject, okay, exchanged all the accept and reject. Then what do I see? I still see one accepting path, right? I see still one accepting path, and the acceptance condition is still same. Even if there is one accepting path, I will still accept. So then I'm saying that, oh, x belongs to L bar also. But how can it be that an element belongs to the complement of the language also, the language also, and the complement of the language also? There's a problem here, right? So this approach will not work. The previous approach will not work. That is why it is still not known whether NP is equal to co-NP. Okay. Oh no. Okay. Okay, I added to the previous. Okay. Now here's another set of questions about P, NP, and so on. Which of the following statements are true? It is known that every language in P belongs to NP. It is known that every language in NP belongs to P. It is known that every language in P can be decided in exponential time. So, statement 1 is clearly true. It is known that every language in P belongs to NP. I have shown this earlier, right? This is true.
Yes, sir.
Right. Now,
Yes, sir.
it is known that every language in NP belongs to P. Is what do you think, Akshay? Is statement 2 true? It is known that every language in NP belongs. No, right? Because if every language in NP also belongs to P, then P would be equal to NP. They would be identical sets, right? But that is not known as of now, right? So yeah, good. So statement 2 is false. So, okay, so we are only left with statement C as a possibility, but we'll still look at statement 3. It is known that every language in NP can be decided in exponential time. By exponential time, I mean deterministic exponential time. And this is actually true. I think it is mentioned in the lectures that how, again, I'll go back, okay. How does an NP language look like? I mean, non-deterministic machine work. It works like this, right? There are two ways to interpret it. One way to interpret it would be like this. There is a I keep making guesses on the way, and there are possibilities. Okay, 0 1 0 1 0 1. I make non-deterministic guesses, just like in the DFA, and I could accept, reject, and if there is even one accept, then I would accept. And there are so many possibilities, but the time it takes on any non-deterministic path is always polynomial. It would always take polynomial time on any path. Okay. Now, what I'll do is, I want to make a deterministic machine for it. That is, I don't want to make all these guesses, okay? I want to make a deterministic machine for it. What I'll do is, I'll do a DFS. I'll explore this path first and check if it lands in an accept. Let's say it did not land in an accept. Then I'll check the other path. I'll check if it lands in an accept. It did not land in an accept. I'll check the other path. It did not land in an accept. Finally, I encounter a path which lands in an accept, and finally it is it lands in an accept, and then I'll accept the language, because then I'm simply exploring all the possible non-deterministic paths. Okay, so I'll just explore all paths, and how many paths are there? And as many paths as 2 to the power poly n. How can I see it? Well, if I interpret it as 0 0 0 0 and so on till here 0, and here 0 0 0 and 1 and so on, how many strings, number of strings of the form 0 1 to the poly n, right? So the string could be 0 0 0 0 0 or 0 0 0 0 0 1 and so on. These are all the possible paths that we take, and there are so many strings, and therefore I'll say, okay, I'll explore all these many paths and check whether it accepts or rejects, and this is exponential, but my machine is still deterministic. Remember, the construction I just did going over each possible path did not have any guessing involved here. Since we are going across all the guesses individually, we are not doing any non-deterministic guesses, so it takes exponential time. The other way to interpret it is, remember that I said that a non-deterministic polynomial L is in NP, okay, means that there is a polynomial size, okay. Alternate answer. Alternatively, L is in NP means that there is a polynomial size certificate that can be verified in polytime. Okay, certificate Y. That means that if X is in L, then there exists a V which is deterministic polynomial time verifier. Okay, by verifier I mean a Turing machine only, such that given X and Y, this will accept. We'll do more on this. Basically, what you want to do is, since the polynomial size certificates are actually just strings of polynomial length, Boolean strings of polynomial length, I'll just go across all possible certificates. And how many such certificates will be there? 2 to the polynomial n, 2 to the poly n. And I'll just go across all certificates. If I find a good certificate, okay, I run the verifier each time. If I find a good certificate, then I'll accept it. But we'll do it that more in detail. It's okay if that's fine. If this certificate definition is not clear, then it's okay. We'll do it in depth. Okay. But anyway, statement 3 is also correct, so C is correct. Okay. So Akshay, is that fine?
Yes, sir.
Okay. Now we'll do more on certificates. Okay. Okay, I'll quickly try to complete this because yeah. Okay. Now, question says, are the following languages in NP? Given a number n, check if it is composite. Okay. Okay. Given a number n, check if it is composite. Okay. What would be the trivial algorithm? How would you check if a number is composite? The simplest algorithm.
It can be multiple of 2.
Can be a multiple of 2. But what if the number given is 25? 25 is
Then
still
it will be a multiple of 5, so it's not a prime. So, okay.
yeah. So given a number, how do I check if it's composite? Well, I can keep dividing by all the numbers which are less than that number, no? Right?
Yes.
So I can divide by, okay, 1 is trivial. 2, if it is not divisible by 2, I'll divide it by 3. If it's not divisible by 3, I'll divide by 4, and so on. But okay, so let's say Akshay, you claim that 32. Okay, not 32. Let's see. 27. Okay, is a composite number. You claim that. Okay, and I tell you that I'm not convinced. Why is 27 a composite number? And you try to prove to me that 27 is a composite number. How would you do that?
But 27 is already divisible by 3, so how can it be?
Yeah, but let's say I don't know that fact.
Then I will show that it is divisible by 1 and by itself. So it can be.
I don't know it, but you need to convince me that 27 is composite.
So
yeah.
It is divisible by 1 and 27 itself.
Yeah, if you tell me, then I'll tell you, oh, then 27 is a prime. But how do you tell me that it's composite? 1 itself, and you said what? It is divisible by 3, right?
Yes, sir, to prove that if it is composite.
You'll tell me it's divisible by 3, right?
Yes, sir.
And further, you can do better also. You can also tell me it is divisible by 9, right?
Yes, sir.
Or in other words, you can also tell me that it is the product of 3 and 9.
Yes, sir.
Yeah, you can give me 3 and you can give me 9, and you can tell me that if I multiply 3 and 9, then I will get 27, and that is why it's composite. That is what you can say, right?
Yes, sir.
And I'll be completely convinced. I'll just multiply them together and then I'll say, oh, this is 27. I'm convinced. Good job. So this 3 and 9 is what we are talking about as certificates. Okay. 3 and 9 is a certificate for the fact that a number is composite. It certifies that 27 is composite. Not just any number, but 27 is a composite number. Okay.
Yes, sir.
So given n such that n is composite, n can be written as a product of a1, a2 and so on, such that a1 times a2 times a3 is equal to n, and these ai is not equal to 1 and ai is not equal to, none of the ai is equal to 27, otherwise I cannot differentiate between them. Right.
Sir.
Right, but so I can just, so what you do is, so given n as input, certificate of n is simply a1, a2 and so on till some ak. Okay, and this is always of polynomial size, because how many numbers can I have from 1 to n? I can only have n numbers, no, which is polynomial. And then you multiply, and then what I'll do is, what does the verifier do? Verifier just does multiply a1, a2 and so on till ak, check if a1 times a2 times and so on till ak is equal to n, then output yes, otherwise no. So I have a small size here. Small size, what do I mean? A polynomial on the size of input. Okay, and so I have polynomially many what do you call factors. Okay, and you give me that, and what I'll do is I'll just multiply them. My verifier algorithm is just multiplying, so this can also be done in polynomial time, deterministic polynomial time. Just the high school method of multiplication will just take polynomial time. It's not going to take exponential time, and therefore it'll say yes or no, and I have this certificate. If I have this certificate, then it is in NP. So given number, checking if it is composite is in NP. Let me call the language composite. Getting it? Is it clear?
Sir.
Okay.
Yes, sir.
Yeah. Okay. So the certificate is just a set of all thing. Set of all factors. Okay. Now next, given a graph, check if there is a Hamiltonian path in G. Okay. Given graph G, check if Hamiltonian path exists. Let's say G is given as an adjacency matrix. Given as an adjacency matrix. Now check if Hamiltonian path exists. What is meant by Hamiltonian path? Hamiltonian path is a path in a graph that visits all vertices. So having such a path is not always known. Okay. And example, sorry, not all vertices, should be visits all edges. Okay, so for example, this graph does not have an Hamiltonian path, because as I try to visit this edge, okay, after this I go to this edge, and then I go to this edge, this guy does not remain visited. So this is not a no Hamiltonian path. Whereas if my graph looks like this, then I can have a Hamiltonian path. I can start here, 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 then here. All the edges I've visited. Okay, by all that visits all edges without repeating edges. Okay, I must not repeat edges. That is the rule. So yeah, otherwise I could have just repeated this guy, and then come back here. It does not make sense to repeat edges. Okay, so all edges visited. Now, let's say Akshay again. I give you a graph. Sorry. Yeah. Okay. You have a graph, and you tell me that uh, there definitely exists a Hamiltonian path here. Okay. You tell me, and you need to convince me that there exists a Hamiltonian path. So how will you convince me? In a given graph, you say that okay, there definitely exists a Hamiltonian path, and I tell you I don't believe you, and you want to convince me. Then how will you convince me? Any idea?
The edges are not repeated itself but while connecting,
But in
and
the edges are not repeated in what?
while connection from one part to another.
Okay, okay. But what is the thing that you'll show me? You tell me that okay. Uh, you tell me that uh, the edges are not repeated. Okay, and but I say okay, but I'm still not convinced. You know a path that the edges are not repeated. I can verify if the edges are not repeated, but you still need to tell me where I should check, right?
Yes.
So what will you give me? You will give me the path itself. Getting it? If you know that the Hamiltonian path exists and you know where it is, you'll give me the path itself. Okay, you'll tell me. Okay, you'll tell me that this is 1, 2, 3, 4, 5, 6. Okay, and you'll tell me check in this order. Check in
You
this
can
order.
reverse it from 6, 5, 4, 3, 2.
Yeah, you can reverse it also. You could have told me that check in this order also, and I would check it in this order. Okay, I'll say okay, 6 is visited. Okay, 5 is visited. I'll maintain a storage space to check what is visited also. Okay, because I don't want to repeat edges. Okay, 6 5, then 5 4, then 4 3, then 3 2, then 3 1, and I'll say oh okay, you are correct. Okay,
But it is touching from 2 to 5 and 5 to again.
it is touching from 6 5.
2 to 5 and 5 to. So it was already repeated from 6, 5, 4
Okay,
and
let's see.
2, 5
6 5 4 3
and 2, 1.
2
2, 5, 1.
2 5. Oh, okay. Repeating, yeah, sorry. Repeating what I should have mentioned. Repeating vertices is allowed. Okay.
Okay.
Repeating edges is not allowed.
Okay.
So yeah, I agree that 5 is repeated, but this is allowed in Hamiltonian paths. Okay. And then we reach 1. And yeah, this is still valid. 6 5 4 3 2 1 is also valid. Okay. So this is what you will tell me. And what is the input and what is the size of this? What is the size of the path that you say? The maximum size is number of vertices, right? And which is still less than the size of the graph. Which is nothing but my input size. Because the input was a graph. Correct.
Yes, sir.
The input is the size of the graph. So since this is the input size and the size is the size of the certificate that you give me is smaller than the input size, it is still polynomial on the input size. So the certificate of the size is still polynomial on the input. The input is what? The graph itself. So I have a small certificate and the procedure is just going one by one and checking, and this will take polynomial time. If you write the algorithm, it will take polynomial time. It won't take exponential time. This means that Hamiltonian path is in NP. Okay.
Okay.
Okay. So here's another one. Given a Boolean formula f, check if it is satisfiable. Okay. Given a Boolean formula f, check whether it is satisfiable. So what does the Boolean formula look like? It looks like and, or, not, and so on. And here x1, x2, x3, and so on. Or you can also represent it like this: x1 or x2 and x1, or x2 bar and x1 or x3. Okay, this is an example of a Boolean formula. Okay. Now, what is meant by satisfiable? F is satisfiable if there exists a satisfying assignment. Okay, there exists an assignment where f of that assignment, I'll call that assignment alpha, where if I assign, okay, alpha equals, let's say, alpha 1, alpha 2, and so on till alpha n, and f contains x1, x2, and so on till xn. These are the variables on which it is on, and f of x1 equals alpha 1, x2 equals alpha 2, and so on will yield 1. So example, say f is x1 and x2 and x3. This is satisfiable. Why? When alpha equals 1, 1, 1. Okay, because if I assign if I do f of 1, 1, 1, which means x1 equals 1, x2 equals 1, x3 equals 1, then it is 1 and 1 and 1. Since and means both the inputs should be 1, then this is equal to 1. Clear, right? Satisfiability is clear. Is it clear what satisfiability means? If there is even one input on which evaluating the formula I get a 1. Akshay, can you hear me?
Yes, sir.
Yeah. Is this clear or should I repeat it once?
Can you please repeat the last point? Yes.
Sure, right. So given formula is this, okay? You get it what a formula means, right? It's just a combination of ors and ands.
Yes, sir.
Yeah. So now the question what I want to ask is, give me an assignment, okay, where this formula evaluates to a 1. This formula evaluates to a 1. And if you assign x1 equals 1, x2 equals 1, x3 equals 1, then f will be equal to 1 and 1 and 1, which will 1 and 1. Okay, if what is the property of AND gate? It will give a 1 if both the inputs are 1. So both the inputs are 1. So this will become 1 and 1. So here also another AND gate, which means it will output a 1 if both the inputs are 1. So this will give a 1. Okay, I'll give you another example. X1 and X2 or X3 bar. Okay. Now, I ask you, is this satisfiable? Well, you will say, okay, assign set X1 to 1. Okay. Set X2 to, okay, let's say this, it's like this. Set X2 equals 1 and X3 equals 0. That's what you say. This will mean F equals 1 and 1, or X3 is 0 complement. What is 0 complement? Nothing but 1. And this guy is 1 or 1. And or means that at least one of the inputs should be 1 to give a 1, right? So this will give a 1. And this is a satisfying assignment. Well, another satisfying assignment could be X1, X2, X3 equals 1. This is also valid. Why? Because F is equal to 1 and 1, or 1 complement, which is 0, which is nothing but 1 and 1 would mean, and means that both the inputs are 1, then output a 1, or would mean if any one, okay, so or 0. If any one of the inputs is 1, then output a 1. At least one of the inputs here are 1, so we'll output a 1. Okay.
Yes, sir.
Clear, right?
Yes, sir.
So anyway, I give you a formula now. Say X1 or X2 or X3, let's say. Okay, I give you the formula X1 or X2 or X3. Now I ask you, is this formula satisfiable? Then and you say yes, and I say I'm not convinced. How would you convince me? So what is the property of OR?
If all,
Yeah,
if all are 1, then it is positive.
if all are 1, good. If all are 1, then F is equal to 1. That's right.
Yes, sir.
So the trick is that given any formula, to convince me that it is satisfiable, you just give me a satisfying assignment, right? Then I'll check.
Yes, sir.
But if the formula was not satisfiable at all, then no matter what kind of assignment you give me, I will check it, and then it would never satisfy it, right? If the formula was not satisfiable, and you would not be able to fool me. But if the formula is satisfiable, you would definitely be able to come up with a certificate with a satisfying assignment, right?
Yes, sir.
It would always exist, and that is the certificate here. Okay. Certificate is a satisfying assignment, which is nothing but a string which is equal to a string of length n if there are n variables, inputs to f. For n formula f, if there are n inputs, then you will just give me an n length bit string of zeros and ones, where I'll just correspondingly plug the values, then evaluate f. Now this is a bit subjective, but if f, this requires an argument, but if f is of polynomial size, evaluation will also take polynomial time. And if f is of polynomial size, the inputs will always be smaller than the size of f, right? F is very big and it contains the input also, so the number of the input is also is of smaller size than f, and if f is of polynomial size, and if input is of polynomial size of f, then the string of length n is also of less than polynomial size, and therefore the certificate which is of length n is of polynomial size. Okay, so certificate is of polynomial size on the given input, and it can be verified also easily. I'll just simply evaluate the function f on the certificate that you gave, and I'll check whether it's yes or no, and then I'll decide the language. Okay, so this is about certificates, and okay, this is the final problem. I would like you to try it. Given a graph G and a number K, check if there is a clique of size K. A clique is a set of vertices where all vertices are adjacent to one another, each other. Okay. Or in other words, it's a small complete graph. Anyway, try that question E and check out the lecture on CNF, and you may try this final question also on DNF. This is try to come up with an algorithm, whether it's in P or not, and if not, I'll solve it in the next. This question I'll solve it in the next session. Okay, we are already reaching 8 o'clock, and therefore we'll terminate the session. So, is that fine? Any questions? Sure.
No, sir.
All right. Okay, I'll stop the recording.